Okay, yesterday in my previous lecture, I have discussed about that how the resistors can be connected in an electrical circuit. There are two ways of connecting the resistors in an electric circuit. One is by connecting them either in series and in parallels. For example, what you are viewing on your screen is the parallel combination where all the resistors have been connected to a common point. All the resistors in this, you can say the electric circuit diagram, have been connected to a common point. This combination we call as resistors in parallel. We have already discussed that the equivalent resistance, if we calculate in series, it is summation of all the resistances. Like it is the summation, for example, in RS will be equal to R2 plus R3, R1 plus R2 plus R3. It means that if we connect the resistances in series, then the equivalent resistance offered by the circuit will be sum of all the resistances. And here again, in case of parallel, if we connect the resistances in parallel, the equivalent resistance is the reciprocal of the sum of all the individual resistances. That is 1 upon Rp is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. We have already discussed that when we have to lay the circuit of our home, what we tend to do? We tend to lay all the resistances in parallel circuit. We try to lay the resistance of a room, all the resistance which are present within the room in the parallel circuit, so that the overall resistance offered by the circuit is less. Now today, what is our topic for discussion? Today, the topic for discussion is the heating effect of current. And what is meant by heating effect of current? For example, there are the two resistors which are shown on your screen. There we are having in one of the resistors are connected in series, and in another the resistors are connected in parallel. Now when the current flow through the resistors, what happened to it? For example, whenever a current is passed through this conductor, I am having a conductor like this. What I am going to try, whenever I will plug it, I will apply the potential difference to it. There are the two terminals. You can see whenever I will apply the potential difference and current will pass through this conductor, over a period of time, the conductor will become hot. Why? What is the reason that why the conductor becomes hot? The conductor, this heating of the conductor, when we pass the electric current through it, this is known as heating effect of current. You can see there are various appliances like electric bulb, electric furnace, electric iron, electric heater, etc., which are based on this effect only, that is the heating effect, which work based on this effect, that is the heating effect of current. That is when the electricity passes through this wire, the wire becomes hot because the electrical energy which is passing through this wire gets converted into heat, and this effect is known as heating effect of current. has to be noted that heating effect may be desirable in some of the electrical instruments, but in various electrical instrument, heating effect is undesirable also. Like in case of electric motor, electric generator, or a transformer, even TV and refrigerator. The the heating effect which has been produced because of the passage of the electric current through the wires is undesirable, right? Okay, here the heat energy is, just a moment. Okay, now I have already told you that once the current flows through the conductor, once the current flows through the conductor, what happens over a period of the time, if the current flows through the conductor will become hot, and this effect of current is known as heating effect of current. This we have already discussed. Now we will try to find out the reason that why such thing happens. What is the reason? I'm starting the yes, I was discussing about that when the current flows through the conductor, it becomes hot. Now, what is the reason for it? We have to find out the reason for it. Let us understand through it. For example, if this is the conductor which is in my hand, this is the conductor, and let me allow the current to flow through it. Okay, once the current flows through it, what happens? You know that there are free electrons which are present in this conductor. When it is connected to the potential difference across the ends of the conductor, these electrons begin to drift from higher potential to the lower potential. Let me make you understand on this. I have told you that once you connect a wire to the potential difference, for example, this is the wire which we are talking, although these are also conducting wires. Now, through this wire, I would like to explain it to you. Okay, I was saying that metal are having free electrons. Metals are having free electron. When we are not connecting it to the potential difference, these free electrons, these electrons move randomly, zigzagly in any direction, right? They move in randomly, they move in any direction. Now what happens? Once we attach, once we apply, once we supply the potential difference to it, when a potential difference is applied across the ends of the conductor, when the potential difference is applied across the ends of the conductor, what happens to these free electrons which were moving in any direction? These electrons, what happen? They start drifting in a particular direction. These electrons start drifting, start moving in a particular direction from higher potential to the lower potential. Higher potential is positive and lower potential is negative. The motion of these electrons, let me tell you, is not smooth. Once we apply the potential difference across the ends of this conductor, these electrons which are present in this connector will move from higher potential to the lower potential. But this motion will not be smooth. Yeah, it will not be without any hindrance. There will be definitely a hindrance, and that hindrance is inbuilt ability of any metal, what we know as resistance. And in order to overcome that resistance, the electricity has to do the work and that work done is converted into heating, right? So I hope this much be clear to you that the electrons which are moving in the conductor is not moving smoothly. Instead, they experience a resistance on account of their collision with the other electrons, right? The resistance is because of their collision with the other electrons, okay, and also with the ions which are present within this conductor. As a result, the work has to be done to overcome this resistance, and this work done is converted into heat. It is this work done which is converted into heat. So it has to be noted that greater the number of electron flowing per second, greater will be the number of collisions and greater will be the heat produced. That is why alloys are the one which are used in those electrical instrument where heating effect is desirable, because their resistance is more, right? Where the resistance is more, the heating effect will be more. Why? Because the collision among the electrons which are drifting apart are more, because the resistance offered by the metal, by the alloy, will be more as compared to the metals. That is why you must have seen that those electrical appliances like heater, like geyser, like this electrical press, the element which is used for heating is made up of alloy rather than a metal. Why? Because alloy has more resistance, and in order to overcome the resistance, the electrical energy consumed will be converted into heat, right? So this relation, where we see the relation between heat produced, current, resistance and time. So the heat produced, where we can see the relation which expresses the heat produced in a conductor and relate it with the current flowing through the conductor. It will relate it with the resistance in the conductor, and it will relate it with the time. That we call as Joule's law of heating, right? Like heating effect of an electric current, yeah, heating effect produced when the current flows through the conductor depends upon the strength of the conductor. It will also depend upon the resistance of the conductor, and it will also depend upon the time for which the current is flowing through the conductor. And this law which provide the relation, which provide the, you can see the relation between all the three: heating effect, current flowing through the conductor, resistance offered by the conductor and time, that is discussed at, that is called as Joule's law of heating, where we say heat produced in a conductor, if current I flows through the conductor whose resistances are, and for time t, the heat produced in the conductor will be directly proportional to square of the current, resistance and time. Now, how can we reach to this conclusion that heat produced in how conductor is directly proportional to square of the current, resistance and time? That I am going to discuss now. As I have told you that when the current will flow through the conductor, what will happen? The work will be done in order to overcome the resistance, and the total work done by the current in an electric circuit, the total work done by the current in an electrical circuit is called as electric energy, right? So the total work done when the current flows through the conductor, and in order to overcome the resistance offered by the conductor, the work done for that is called as electrical energy. Now to calculate the electrical energy, let's see what we do. Let V be the potential, right? For example, if there is the circuit where the current is flowing through a particular resistor, here voltmeter, this is the ammeter, okay? If V is the potential, let current I flows through the conductor for time t, okay? And Q be the charge flowing through the conductor during the time t. Q be the charge, amount of charge flowing through the conductor, be Q for time t, right? Then what will be the current flowing through the conductor equal to? Current is equal to charge upon time. Let I be the current, then Q be the charge and T be the time. So what will be Q equal to? Q is equal to I into T. Q is equal to I into T. What we are trying to find out, that how we have reached to the conclusion that the work done is equal to, or the heat produced in a conductor is I square RT. This is our you can say aim, is to find out that how work done in the conductor is equal to I square RT. This we have to reach down the conclusion. We have to find out this. For that, what we are trying to find out, that if Q be the charge which is flowing through the electric circuit for time t, then current is I is equal to Q upon T. Then what is Q? Q is equal to I into T, right? Now, as you know that the board is Q is equal to I into T. Let this be equation 1. Okay. Now, as you know that in order to overcome the resistance, work has to be done in the conductor in the form of which will be converted into heat, right? If W is the amount of work done when the charge Q flows from one end to another end of the conductor, then what is V equal to? As we know from the definition of potential difference, amount of work done in moving a unit charge from one potential to another potential. Okay, so what will be here? V equal to, if Q is the amount of charge flowing in the conductor for time t, then work done will be in terms of heating effect of the current. That work done we can, okay, that V is equal to work done upon quantity of charge Q. From the from the definition of potential difference, I know that what is definition of potential difference? When the work done in moving a unit charge from one potential to another potential, then V is equal to W upon Q, right? But what will be this work done equal to? Work done will be equal to V into Q, right? This is equation number 2. Okay. W is equal to V into Q. Now, from the equation first, what is Q equal to? From the equation first, Q is equal to I into T, right? What is Q equal to? It's I into T. And even from the Ohm's law, according to Ohm's law, V is equal to, what is V equal to according to Ohm's law? It is I into R. Okay, this is equation number 3. Okay, substituting the value of equation 1 and equation 3 in equation 2. Substituting the value of, let me admit them. Okay, substituting the value of equation 1 and equation 3 in equation 2. So what will be the work done? Work done which is in terms of heat produced. So the work done will be equal to I into R, and what is Q? It is I into T, right? You know, in mathematics, anything raised to power 0, we consider it as 1. And in math, there is one more conclusion that if the bases are same, powers are to be added. So what will here, the base of I and I is same, so their powers will be added. So ultimately our equation will become like this: W is equal to I into R into T. W is equal to I into R into T. I will once again make it understand. I have told you, let current Q flow, let charge Q flows in an electrical circuit for time T. Okay, I be the current flowing through. Okay, then what will be current equal to? Current, as per the definition of the current, it is rate of work done. That is, I will be equal to Q upon T. So what will be Q equal to? Q is equal to I into T. That will become our equation 1. Okay, you know that some work has to be done because each and every metal will offer some resistance, and the work done in order to overcome the resistance will be in terms of heat. So here what we will say that if W is the amount of work done in carrying Q charge from this potential, positive potential, to the negative potential, then according to the definition of the potential difference, then V is equal to work done upon quantity of charge, Q. So what will be work done equal to? It will be V into Q. Work done is equal to V into Q. Now, but according to Ohm's law, what is V equal to? V is equal to I into R. Now, substituting the value of equation first and equation second. So, equation first and equation third. In equation second, what we will be left out is W is equal to I into R into I into T, where bases are same, powers needed to be added. So W, work done, which is in terms of heat produced. So we can say that heat produced in a conductor is equal to I square RT, which is also known as Joule's law of heating. Okay. So here we can have different values for V. Substitute the value of I from the Ohm's law. Okay, once we substitute the value of I from the Ohm's law, our ultimate, let me show it to you how it has to be done. So now we have reached to this conclusion that heat produced in a conductor is equal to I square RT. But according to Ohm's law, I is equal to V upon R. You know about it. I is equal to V upon R. Substitute the value of I in equation 1. So what will be our equation 1? It will be H is equal to V upon R square, because here current is I square. So substitute the value of I from Ohm's law here. So it will become V upon R square into R into T. So one of the R can get cancelled with one of the R. So what will be H? It will be equal to V square into T. V square upon R, because only one of the R will be cancelled because there are square R into R. One of the R will be cancelled. So H will be V square upon R into T. In the same manner, if we substitute the value of R from Ohm's law, we will get W, yeah, heat produced will be in terms of again V square upon R upon T. Then we can substitute the value of R. R is equal to, yes, from the Ohm's law we can substitute the value and we can get the different values. H is equal to V into I into T. H is equal to I square RT and H is equal to V square upon R upon T.